Welcome, Unit 6, the first episode of the Flipped Classroom for the 2016 year at Duncan Macmillan. Welcome to Unit 6. This is linear equations and inequalities. For 6.1, we're going to be talking about solving equations, specifically using inverse operations. So our learning goal to start is I will model and solve linear equations. And we have 5 success criteria that go along with this. First, I can model a linear equation. So you can write it out, you can display it, you can put it in picture form. I can verify my solution with substitution. So we're going to be able to check and solve our answers. Thirdly, I can solve a problem symbolically or algebraically. Likewise, you can solve a problem pictorially. There's a picture option when you're solving here for this block. So that is the second option. And lastly, I can record my steps to show my work. So let's get into a little bit of review here. So let's just review simplifying expressions. We have to think about BEDMAS. So brackets, exponents, dividing, multiplying, adding, and subtracting. Essentially for this section, we're going to be solving equations using inverse operations. So what's the big idea that you can get from this? Is that first off, a linear equation can be true for only one value for the variable. So let's say if we have an equation set up and it equals something, that's why it's an equation, it's only going to be true for a certain number. Okay? All linear equations, so let's say like x will equal 3 when the problem equals 9. Okay, so that x or that variable does have a certain value for the specific problem. And we'll get into more of that so that becomes more familiar. And then linear equations can be built by applying operations and can be solved by applying the inverse operations in the reverse order. And this is really our big key for today to understand here as students. This one right here. Okay? That's really, really important, okay? So that we understand problems can be built. Okay, so like you have a variable and you add on to it. But then likewise, you can also undo it. You'll see that your textbook refers to a car tire to be exact. So it talks about how to remove the tire by putting on the jack and then loosening the nuts and then taking the nuts off and then taking the tire off. Well, the problem is solved then by putting a new tire on and then tightening the nuts and then lowering the jack and then you're good to go. So it's just the opposite set of operations. So that's what an inverse operation is. So an inverse operation means to undo or reverse the results. So inverse operations, so the opposite of addition, subtraction. Opposite of multiply is divide, and the opposite of squaring is to square root. And likewise the other way around. So if you saw that we had x and it was subtracted by a number, well, you would add by that number in order to solve for it. Or likewise, if x was being divided by a number, you would multiply to undo it. Okay, so we can solve using inverse operations. Okay, and that way we can solve that either symbolically or pictorially and then show our work. So your sheet says, remember, to solve the equation, we need to isolate the variable, okay? And we can solve this by undoing the operations that are applied to the variable. So let's take a look at 3 quick examples of inverse operations. So, for example, we have x plus 3.7, and that equals 9.2. So what has happened in this case is we're going to identify the operations that are applied to x. So if we take a look at x here, so we can see that added to x is 3.7. Okay, so that's where they're getting x plus 3.7 equals x plus 3.7. And that's what we have here on the left side. So on the right side of this equation, 9.2, kind of similar to that car type example where you had that tire and then you remove the tire. Now you're just going to put one on. on. So just kind of like the reverse operation. So rather than adding 3.7 to 9.2, we're going to subtract it, and that's how we get 5.5. So since x plus 3.7 is equal to 9.2, if we get x by itself, or isolate for it, we can apply the inverse operation to the 9.2, so we can subtract 3.7, and therefore it equals 5.5. So here we have questions 2 and 3. Take a look at question 2. We have negative 3x. So what's happening to the x? X is being, and I know it's really similar. This is an italicized s, or x. So we're multiplying x by negative 3. That's how we're going to get negative 3x. That's what's on our left-hand side. Down below is what's on our right-hand side. So this is down over here. So we have 9. Obviously, the opposite, the inverse operation of multiplying by negative 3 would be dividing by negative 3. And 9 divided by negative 3 would be negative 3. Okay, and if we take a look at question 3, x is being divided by 5. So x divided by 5. That's what happened to x. So we can do the inverse operation to the 3. 3 multiplied by 5. 3 times 5 is 15. And that would be the answer for x there as well. Okay, so it's really important to understand that those were equations, linear equations that were built. Okay, so for example, just a flashback, x was multiplied by negative 3. X was divided by 5. X, there was 3.7 added on to x. So these were being built together. So if I wanted to go ahead and solve this algebraically, so that was the actual pictorial method. The algebraic solution for number 1 would be x plus 3.7 equals 9. And we have to do this inverse operation to each side. I'm just going to show this with red ink. So we're going to actually subtract 3.7 to the left side. And if I do something to the left side, I have to keep this equal and proportionate. So if I do it to the left side, I also have to subtract the right side as well. So now these would cross out, because I had 3.7, take away 3.7, that's nothing. So x equals your 5.5. Okay, for question 2, very similar. I had negative 3x equals 9. So right now I can see this and see x is being multiplied by negative 3. So I can go ahead and I can divide each side by 3. That's the inverse operation of multiplying. Oh, and instead of just dividing by 3, I can divide by negative 3. So now what I can do is negative 3 divided by negative 3 is 1. So I'm left with x. And 9 divided by negative 3 is negative 3. And then lastly, question 3, we have x over 5. That just means x divided by 5 equals 3. Okay, and for this one here, I'll just use blue. So x is being divided by 5. So the opposite of divide by is multiply. So now those would cross out. And I would be left with x equals 3 times 5, 15. Okay, so that's the first step here. Now let's try a couple other ones that are a little bit more difficult, because there's a couple things going on at once. So we're going to start off with what are we talking about here? Our subject is x. So what is happening to x? Well, x is, first off, we're just going to do this like bed mass, okay? So x is being multiplied. X is being multiplied by 3. Whoa, Silas is not working today. So x is being multiplied by 3. So that would leave me with 3x. Then I will be subtracting 5. which is going to be with 3x minus 5, or subtract 5. That's good. That's what I want on my left side there. Now I'm going to start out on the right with what I have on the right. So I have 7. And now I'm going to do the opposite of bed mass. So I'm going to do the S-A-M-D-E-B, I guess. So I'm going to do the opposite. So the last thing I did here was subtract 5. So I'm going to add 5 to each. So 7 plus 5 is 12. Okay, and see here, up here I multiplied by 3, so down here I'm going to divide by 3. 12 divided by 3 is 4. Now if I want to show this algebraically, I could say 3x minus 5 equals 7. So I'm going to add 5 to each side, which leaves me with 3x equals 12. Divide each side by 3. X equals 4. Okay, I'm done. So now let's finish that last one off. So we have x. What's happening with x here? So it's x over 2. So in this case here, I'm dividing this by 2. So that's how I get x over 2. Now I'll rewrite that a little bit better here. 1 second. Voila! There we go. X divided by 2. And now what am I going to do to this here? I'm then going to add 2, just like over here. So now I have x divided by 2 plus 2. And on the right hand side, I have negative 5. And then I just added 2, so I'm going to subtract 2. Which leaves me with negative 7. So now I have negative 7, and then times 2. So negative 7 times 2 is going to be negative 14. So let's take a look at our algebraic solution. So we'd have x over 2 plus 2 equals negative 5. Why is that not working? There we go. Okay, so first things first, I'm going to subtract 2. Okay, you have to do that operation first. It's really important that we get that clear. So whatever was the last thing you really did, whether it was add or subtract, to the left-hand side, you have to do the opposite of that, the inverse of that first. So that gets me x over 2 equals negative 7. And then here, I'll do this part in red. X is being divided by 2, so I'm going to have to multiply both sides by 2. So that my final answer will be x equals negative 14. Okay. Now, it's really important to be able to take a look at one of our other parts of the success criteria. If I go back to the first slide, so we did solve pictorially, we did solve symbolically, we modeled this linear equation by just writing it, and we did show our steps. Now, how do I verify my solution with some substitution here? We got 1 minute to finish this off. So if I take a look at my last question, well, we have our last question, x over 2 plus 2 equals negative 5. We got x equals negative 14 as an answer. So let's check this to make sure that this is true. If I put negative 14 in for x, will this equal the same amount on both sides? Negative 14 divided by 2 is negative 7. Negative 7 plus 2 is negative 5. And that does equal negative 5. So that's exactly what I want. Both sides are equal, and therefore we've proven one of the cases that a linear equation can be true for only one value of the variable. So that's it, and we'll continue on with the second part. Part 2 of 6.1 is up next.